On this tape, we're going to look at equations involving radicals and method for solving such equations. Let's look over at just some examples of what we mean by that. Equations involving radicals, or sometimes we call them radical equations. Here are 4 examples of that type of thing. Square root of 3x plus 1 equals 4. The square root of x plus 8 minus 2x equals 1. The square root of 1 minus 2x plus the square root of x plus 5 equals 4. And then notice the number of radicals keeps increasing. And then finally, we've got an equation with 3 radicals. The square root of 2t plus 5 plus the square root of 2t plus 8 equals the square root of 8t plus 25. Notice the variable happens to be t in that one. No particular reason, just happens to be that. Well, just a brief review of solving equations. Remember what you know about solving equations. If you'll look over on the pad here a second, we've got, suppose A equals B in an equation and C is positive, then the following are equivalent equations. I'm reminding you of these are really the 4 things that you know how to do, how to manipulate an equation. If A equals B is any old equation, maybe the ones I just showed you, and C is any positive number, then we can add C to both sides of that equation and not change its solution. Remember, equivalent equation means that this equation that I get by adding C to both sides is equivalent to that one, means it has the same solution. Or I can take that positive number and subtract C from both sides, and I'm still assured that this new equation I get by doing this will have the same solution as the original one. Or I can multiply both sides by that positive number, and I still have that assurance. Or I can divide both sides by that positive number, and I still have that assurance. It could be extended even further and say that we could divide and multiply here by negative numbers. I just simply chose to think of C as a positive one to illustrate these 4 properties. But we need to, in order to deal with radical equations, we need to add one more property to our arsenal, and that is maybe this statement. Suppose n is a positive integer, then can we do this? Can I take the power of both sides, that is the nth power of both sides, and expect that I'll have an equivalent equation to the original one? That's the question. Well, the answer to that question is no. In fact, let's look at an example to see that. And if you look over on the pad, consider this equation. We'll keep it simple. Remember, I'm thinking a moment ago I was using capital A equals capital B. So capital A just represents the left side of the equation. Capital B just represents the right side. And this is a real simple equation. Capital A is x and capital B is 3. X equals 3. It has solution set, obviously, 3. Now, what about if we let n be 2, and so I want to now consider a squared equals b squared. I want to square both sides of that equation. And that's what I do right here. Square both sides of the equation, and you'll get, of course, x squared equals 9. And it doesn't take much thought to remember that the solution to this equation, this new equation we get, has two solutions, 3 and -3. So, are these two equations equivalent? No, they're not. If they don't have the same solution set, they're not equivalent. So squaring both sides of an equation produces an additional solution. We've introduced an additional solution set. It's solution to the solution set of the original equation, and we call that an extraneous solution to our original equation. We pick up an extra solution that's not a solution to the original one. Or to state that in more general terms, so for each equation in the form A equals B, if you take and look at the equation you get by raising both sides of that equation to the nth power, you may introduce an extraneous solution. So how are we going to know if we have? Well, what we're going to have to do, if we're going to ever do this, is we must always check our resulting solution set for these extraneous solutions. That anytime you raise a power of both sides of an equation, you might introduce an extraneous solution, as that example shows. And so if we're going to do this and add this to our arsenal of things that we can use to manipulate equations, then we must check to make sure that we haven't changed the solution set. So let's illustrate this with an example. We'll look at a fairly basic radical equation, and from this we'll develop a procedure to follow. So I'm going to write down, as we talk about this, I'm going to show the steps that we're utilizing to solve it. We've got ourselves an equation that has a radical in it. So how can we find out what x is? That's what you want to do. When you have an equation, you want to solve it. You want to find x and find all the x's. So the first thing we're going to do is, it says over here, isolate the nth root radical. That's just a shorthand way of saying isolate the radical. That is, if you've got a radical in your equation, we're going to isolate it. We're going to solve for it. So that's pretty easy here. I can use just the basic property of equations and add 3 to both sides. And so we get the radical isolated. Now, what I want to do, well, I'm going to square both sides. I'm going to take that, here's my capital A, here's my capital B, so I'm going to square that left side of the equation, I'm going to square the right side of the equation, and that's what this is saying. You're going to take the nth power of both sides. I'm trying to state these in general here. You'll find that most of the problems you're going to be working is going to be dealing with square root, but let's kind of say it in general. So we raise both sides to the nth power. And we know what happens there. On the left side, we'll get, what are we doing? We're squaring the very number whose square is 2x minus 1. So that's what we get, 2x minus 1. And if you square 3, you get 9. And so we've taken this equation that had a radical in it, and we have now changed it into an equation without a radical. And what we've used is the property of radicals that says that the nth root of A raised to the nth power is A. All right, well, now, no problem. We can just solve for x by the appropriate method. What do I mean? Well, lots of things can happen at this step right here. That is, you may end up with various kinds of equations here. What kind of equation is this one? You should recognize it as just a linear equation. And we know how to solve linear equations. You solve for x, you just go through the appropriate steps. I first solve for the x term and then divide both sides by 2, and I end up with x equals 5. I have solved for x. Now, am I done? Well, in radical equations, we're not done. That is not the end of it. We must check radical equations. We must find out if we have a solution. And the only way you're going to find out that you haven't picked up an extraneous solution by the squaring of both sides is to substitute back into the original equation, which was the square root of 2x minus 1 minus 3. So I've just replaced x with 5, and I go through and simplify until I see it's obviously a true statement. Well, that's obviously true, so these must be true, and so this must be true. And so therefore 5 is a solution, and I can write my solution set, which is my last step. Well, that example's a little misleading because it only has one radical, and it did check, and we'll find as we go through some of these other exercises that as we add more radicals they get more complicated, and but essentially that illustrates the procedure we're going to follow. So let's look at the exercises. Okay, here's the first one, and it's basically the same as one we just did. What did we say we do the first step? First step, we're going to isolate the radical. Well, good news, it's already isolated. So first step is isolate radical, and then square both sides. So we square both sides, and that's what I'm doing here. Now, I didn't say square each term. In this case, it's not too hard to see what both sides are. They're just two terms. And you end up with some type of equation. In this case, a linear equation, and after using the fact that the square root of a squared is a, we just want to solve for x by whatever method is appropriate. In this case, it's just like the other one. Subtract 1 from both sides and then divide by 3. We get 5 again. Or do we? Well, let's make sure. We'll take that number and we'll check it. Of course, checking, is always a good idea. It's just not always convenient. But here, it's not just a good idea, it's a necessity. You must check these. It's part of the method. So we substitute it in to that equation, and sure enough, we get the square root of 16, which is 4. That's a true statement, and so our solution set is 5. Well, now let's look at one where maybe the solution doesn't check. Alright, so we've got a radical, so what's our first step? Well, we isolate the radical. So I'm going to subtract 8 from both sides, And that would leave me then with just the radical equals to a negative 2. And then we said we'd square both sides. And again, let me emphasize, put those parentheses around the whole thing. I'm going to square it over here, whole thing, square it. So if you square the square root of x squared plus 5x minus 2, you're squaring the very number you got to square to get that. So you get x squared plus 5x minus 2. Over here, we get 4. So we remove the radical. Now, solve by the appropriate method. Well, hey, it looks like a quadratic equation. So we know the first step in solving a quadratic equation is to set it equal to 0. And we hope that we can use the factoring method. Well, good news, we can. X plus 6, x minus 1 is how that factors. And so we've got a product equal to 0, so either that factor is 0 or the other is 0. Solve for x equals a negative 6, or x equals positive 1. Maybe. So let's check. Get another sheet of paper here. I'm checking in the original equation here. The original equation, I want to see if x equals negative 6 or if x equals 1 is a solution. So I need to substitute in a negative 6, so that'd be a negative 6 squared plus 5 times a negative 6 minus 2 plus 8 equals 6. Question mark. Is that a true statement? Well, that's what? The square root of 36 minus 30 minus 2 plus 8 equals 6. Minus 32 there. 36 minus 32 is the square root of 4 plus 8 equals 6. Or 2 plus 8, and that certainly is not equal to 6. So therefore this is not true. So therefore x can't be a negative 6 or in my solution set. So this must be an extraneous solution. How about 1? If you put 1 in here squared plus 5 times 1 minus 2 plus 8, does that equal to 6? That's the square root of 1 plus 5 minus 2, and 5 minus 2 is 3 plus 1, again we get 4 there, plus 8, and we already know again that's not equal to 6, so this fails as well. So this fails. So neither one of those turn out to be solutions. So what's our solution set? Our solution set then is empty, right? It's the null set or the empty set, because neither one of these solutions, neither one of these can be a solution. Okay, here's our next one. The square root of x plus 8 equals 2x plus 1. You might want to try this first. Stop the tape. All right, let's do it together. First step is to isolate the radical. Well, that's already done. So let's square both sides. Huh? Again, remember, you're going to put parentheses around everything on the left side, square it, and everything on the right side and square it. And be very careful to do that, and you won't make the mistake of just squaring both terms. That's not what it's saying. It's saying square both sides, the left and the right. So of course we know if we square this square root, we're going to get just what's underneath the radical. Well, look here, when we square this, we got to square a binomial, and so we get, using FOIL or using the patterns, we get 4x squared plus 4x plus 1 equals x plus 8, and then solve by the appropriate method. Well, you should recognize again a quadratic equation. So first thing we want to do is set it equal to 0. The left side is convenient to be 0. We move everything else over to the right. That'll give us 4x squared plus 3x, taking away x from both sides, and subtracting 8 from both sides, we get minus 7. Again, the method of choice for quadratic equations, we hope it factors. Does it? I think so. 4x plus 7 times x minus 1. And then set each of those factors equal to 0 and solve for x. Okay, up here. So solve the first one for x. You've got to subtract 7 from both sides, then divide by 4. And so we get x is equal to a negative 7/4 or 1. And now we need to check it. So let's first check with the negative fraction. Put a negative 7/4 in for x, and it's a negative 7/4 plus 8 equal to 2 times a negative 7/4 plus 1. Well, that's kind of messy, but all you got to do is get a common denominator there of 4. So we need to change that to fourths. 8 is 32 fourths. So you'd have a negative 7 plus 32 fourths, and that's all under the radical. Is that equal to dividing out a 2, negative 7/2 plus 1. And add those together, and that's a negative, or rather a positive 25/4 under the radical, and that's a perfect square. Square root of 25/4 is 5/2, but on the right side we get a negative 5/2. So those aren't equal to each other. So that means then that negative 7/4 is not a solution. How about the other one? Take 1 and substitute it in to into the original equation. And over here you get 9. Over here you get 3, and that's obviously true. So that will be a solution. And so therefore our solution set is 1. Just a quick little warning here. Don't fall into the trap, the thinking that you can guess which solutions work or don't work by how messy they look. Of course, negative 7/4, and this last one was pretty ugly, but you cannot really tell whether the nice number is going to be the solution and the not so nice one is not. It can happen either way. In fact, let's look at the next exercise and maybe we see that very thing illustrated. look over on the pad. Number 4, 2x is equal to 1 plus the square root of 3x plus 1. Okay, again, you may want to stop the tape at this time and try that one yourself. All right, let's do it together. So, first step, isolate the radical. It says it right over there. That's what we're going to do, isolate the radical. Next step, we're going to square both sides. Again, it's stated in general over there, but that's what we're going to do. So we put everything in parentheses on the left and square both sides. On the right side, you get just what's underneath the radical. On the left, you get that square of a difference, which everybody knows is the square of the first minus twice the product plus the square of the second, right? And then that's utilizing our properties of radicals, and we've got ourselves a quadratic equation again, so we set it equal to 0, and it ends up being just a very simple one that factors by just factoring out the greatest common factor of x, and now setting those equal to 0, we get that x is equal to 0 or x is equal to 7/4. Okay, well, let's see which one of those will work. So here's our original equation again, and now let's look at the check. We're going to take those two potential solutions and substitute them in. Put 0 into wherever you have x, and notice the right side ends up being 1 plus 1, or 2, and the left side ends up being 0. So we already know x can't be 0. That's not going to work. Well, let's look at the right side with this fraction. We put 7/4 in place of x. There it is. And 3 times 7/4, that's 3 over 1 times 7 over 4, that's 21/4. And on the left side, 2 times 7/4 is 7/2. 21/4 plus 1, that's 21/4 plus 4/4. 21/4 plus 4/4 is 25/4. There it is. So 7/2 equals 1 plus the square root of 25/4. And that's a perfect square underneath the radical. 5/2. And so 7/2 plus 1 plus 5/2, that's 2/2 plus 5/2 is indeed 7/2. And so this is a true statement. If this is true, then this is true, then this is true, then that is true, which means that 7/4 is a solution to this original equation. And that's what it says. And so therefore, write our solution set, which only contains the ugly number, not the nice one, of 7/4. All right, well, what about an equation that has two radicals in it? The square root of 1 minus 2x plus the square root of x plus 5 equals 4. Well, the method stays the same. We do exactly the same thing. What's the first step? The first step, we got to isolate the radical. So, well, but it's not the radical anymore. We've got two radicals, and so we've got to choose one of them. It really doesn't matter which one you choose. It might be a good idea to pick the maybe the more complicated one to isolate, if there is a more complicated one. And in this case, I chose to isolate on 1 minus 2x, but really either one. And so now you've got a radical isolated, not the radical, but a radical isolated. And we're going to do the same thing we did before. So step 1 was we isolated the radical, right? So I think I'll just write that down. Isolate radical. All right, so now what? Now we got to square both sides. And again, to do that, get in the habit of putting those grouping symbols around both sides. So I'm writing it over, or you could actually do it on this step, but I'm going to show it in the next step here. Put grouping symbols around both sides and square them. You're less likely to make mistakes. So what is that? I'm squaring both sides. Okay? Well, that's easy on the left. On the left side, we get just what's underneath the radical. But on the right side, we've got that, what we looked at on the last tape, a special product involving radicals. It's a square of a difference. It just happens to have one of the terms in that difference is a radical. And so how do we do that? Remember, the pattern is, if you're here, you got a minus b, it's a squared minus 2ab plus b squared. Or just to use grouping symbols, it's the square of the first one minus twice the product plus the square of the second one. And then we can just insert the first one here, the first one there, and the radical in the other two. And does that fit the pattern? It's the square of the first one minus twice the product of the two things plus the square of the second one. Well, let's see how it was written in the next step. Sure enough, there it is. Let me get that off out of the way. And now we've got to use our properties of radicals here. The fact that the square of the square root of a is just a, to simplify this. And so we do that, and 4 squared is 16, and of course 2 times 4 is 8, and if you square this thing right here, you get just what's underneath the radical. But notice, we still have a radical equation. Right? So what are we going to do? We're going to cycle back up and do exactly the same thing again. It said at this step we should be solving by the appropriate method. Well, the appropriate method is to solve it as a radical equation. And what do we do with a radical equation but isolate the radical? And so number 1 is revisited. We go back to number 1, which is isolating the radical. So I moved everything else on the other side. I subtracted x from both sides and got negative 3x. And I added these two together, which is 21, and subtracted that from both sides and got a negative 20. And so now I have the isolated radical, and we've got to do the same thing we did before. And here it is. We've got to square both sides. All right, step 2. We're going to square both sides. Notice at the same time, go back to the other page here a second. We had down here negative 20 minus 3x equals a negative 8 times that. Well, a real obvious thing to do here would be to multiply through by negative 1 and make all those positive, and that's what I did in this step. Made that a positive 20, made that a positive 3x, made that a positive 8. And then square both sides. You don't have to do that, but it's just easier if you do. And now, watch it here. Real tempting to forget that 8, but you're squaring not just a radical anymore, you're squaring a product, so you've got to square the 8, which is 64. You've got to square the radical, which is just what's underneath the radical. It requires that you put it in parentheses. And over here, we're squaring another sum. And so when you square that sum, you're going to use that special property again. It's the square of the first one plus twice the product of the two plus the square of the second one equals to 64x plus 5. And I'm just emphasizing again, that's what I've used, that pattern. There it is. Simplify that. 20 squared is 400. 2 times 20 times 3 is 120x. 3x squared is 9x squared. Distribute 64. You get 64x plus 320. Now you're at step 4, which is solved by the appropriate method. And this time, the equation we got after going through that cycle of steps has no radical. It's just a nice quadratic equation. We set it equal to 0 and hope that it turns out to be a factorable quadratic. 80 plus 56x plus 9x squared. And yes, that does factor. With a little work, we can show that it's 9x plus 20 times x plus 4. Set each of those factors equal to 0, and we get x equals a negative 29ths or x equals a negative 4. Maybe. How do we know? We gotta go check. So, next page. Here's the original equation again. And we're at step 5, which is checking. Here are the potential solutions: a negative 29th and a negative 4. So let's substitute them in. So we substitute in, and let's see if we can get a solution. Notice, every place I had x, I put a negative 29ths. And over here, every place I had x, I put a negative 4. Again, these are awfully messy. Why don't we work this out by hand from here? So let's see. We get the square root of, if you multiply those two together, you're going to get 40 ninths there. And over here you got a negative 20 ninths plus, well, I know I'm going to have to change that to ninths, so let's just go ahead and do it, 45 ninths. Question is this going to turn out to be 4? This is 9 ninths plus 40 ninths gives me the square root of 49 ninths. Over here, a negative 20 ninths plus 45 ninths is 25 ninths. Both of those are perfect squares. The square root of 49 ninths is 7/3. The square root of 25 ninths is 5/3. And if you add those together, you get 12/3, which is indeed 4. So, as ugly as that number appeared, it is a solution. How about the other one? Well, let me draw a line here, separate these. If I multiply those together, I'll get 1 plus 8 out of that one. Add there, I get the square root of 1. That's 9. So it's the square root of 9 plus the square root of 1, which is 1 plus 3, which is 4 as well. So they both check. and I think that's what was shown here. And so since they both check, they both belong in our solution set, and we write it thusly. Okay, here's one like that one we just did for you to try. So pause the tape, copy this one down, and work it out and check it and come up with a solution set, and then we'll work it together. Okay, did you get the solution set to be 21? Well, let's see. First thing we're going to do, isolate a radical. Well, I think I will do it a lot of ways, but since this one's negative, I'm going to move it over to the right-hand side and leave these two on the left-hand side. So I'm going to rewrite this as the square root of x minus 5 plus 1 equals to the square root of x plus 4. And now, next step, we want to, in this case, square both sides, right? So, again, everything on the left side in parentheses, square it. Everything on the right side in parentheses, square it. That's the way to do it, and hopefully not make a mistake. All right, so notice the left side. Again, you've got that special product, a square of a sum. Again, I think if you'll practice this a bit, you'll find you won't even need to do this, but it's the square of the first plus that sign twice the product of the two plus the square of the second is equal to, and this is the easy side, you're squaring the square root of x plus 4. That's x plus 4. And in here, here's the first, then twice the product of the first and the second plus the square of the second. So if you square that, you get x minus 5. Multiply this together, you get 2 times the radical x minus 5. Square that, you get 1 equals x plus 4. Let's collect like terms. That'd be x minus 4 plus 2 times the square root of x minus 5 equals x plus 4. Still got a radical equation, so the appropriate method is to isolate the radical. Well, let's put everything, let's just leave the radical on this side. And we'll move everything else to the other side, so I'll subtract x from both sides, which is 0, and I'll add 4 to both sides, which will give me 8. I've isolated the radical, but I also notice that I have a factor of 2 on both the left and the right side of the equation, and might as well take advantage of that, and when you can, and divide that out. So if I divide this side by 2, or if you want to multiply both sides by 1/2, you'll get just the radical x minus 5 equals 4. And now we have a very basic radical equation. Square both sides. Again, left side in parentheses squared, right side in parentheses squared. That'll give me just x minus 5 on the left, 16 on the right. Add 5 to both sides. Since it's just a linear equation, x equals 21. Maybe. Don't stop there. You've got to go back to the original equation, which is right here. And we want to know, does x equal to 21? Is that our solution? So we substitute in 21 into the original equation, and always go back to the original equation when you do this. Square root of 21 minus 5, well, that's the square root of 16. There's the square root of 25 plus 1. Is that equal to 0? That's 4 minus 5 plus 1 surely equals 0. So this is a true statement. So therefore, my solution set is the 21. Okay, here's another one. Again, pause the tape and try it yourself, and then we'll work it together. So, did you get 1/2 and 13/2? Well, let's see. I need to isolate a radical. Well, just depends on which one you think looks the messier. I think I'll isolate this one. If I didn't pick the one you did, it doesn't matter. Should get the same thing. So I'll subtract this radical from both sides. And notice it's in the variable t here, but don't let that bother you. Just another variable. And now we're ready to square both sides. So enclose everything on the left side in parentheses and square it. Enclose everything on the right side in parentheses and square that. The left side, you get just what's underneath the radical. So that's 4t minus 1. On the right side, we've got to square a difference. Now let's do this, try to do it without using the grouping symbols. We've got to square the first one. There's the first one. Well, that's easy. You get 1. And then it's minus, it's whatever this sign is right here. So minus twice the product of the two. So twice 1 times the radical. Twice the product plus the square of the second one. Well, if you square that, again, you're squaring the very number that you have to square to get 3 plus 2t. So what do you get? 3 plus 2t. Well, that wasn't so bad. But I'm left with a radical again. So I know that I need to isolate that radical. So as I simplify this, I might as well isolate it. So I think putting it over on the left-hand side would be a better place for it. So I'm going to do it that way. This is, of course, just a -2 here. So when I move this whole term over to the left-hand side by adding to both sides its opposite, I'm going to get a positive 2 times the radical 3 plus 2t. And let's just go ahead and just do that step. And add like terms here, that'd be 4 plus 2t. So all I did was combine like terms here and move this term, this radical term, over to the left side. And now I need to isolate it by subtracting 4t from both sides. So what I want to end up with on the left side is just this radical. And you want to remove these. So if you do them one term at a time in your head, you're less likely to mess up. Subtract 4t from this, that makes this go away. Subtract 4t from this, and you'll get a negative 2t. And then add 1 to both sides. Add 1 here, 0. Add 1 there is 5. Okay, again, I have a factor here on the radical, but it's not a common factor throughout the equation. So I wouldn't divide it out. I just leave it on that radical. We've got it isolated, and so our next step is to square both sides. Again, usually, as we did, put them in parentheses. You square the left-hand side. Don't forget to square the 2. Becomes 4 times the quantity under the radical, the radicand, equals, and now you got to square another difference. Square the first one, 25, minus twice the product, 5 times 2t, plus the square of the second one. Let's get rid of the parentheses. That's 12 plus 8t equals 25 minus 20t plus 4t squared. Looks like a quadratic equation, so we know what to do with quadratic equations. You make one side 0. I'm going to make the left side 0. I'm subtracting everything on the left side to both sides. So I'll have 4t squared, subtract 8t from both sides, and that'll make that minus 28t, and then subtract 12 from both sides, and I'll get plus 13. And now we hope that it factors. I think you'll find most of your exercises that when you get to a quadratic right here, if it doesn't factor, I'd be quite skeptical about what's happened. It's kind of a place to check yourself. Alright, so I feel like this is going to factor. Now I know the signs have both got to be minus, and I'm looking for the way I like to say it, a sum of 28. A sum of 28. Well, play around with this. I think it's 2t and 2t, 13 and 1. Here is a negative 26, and a negative 2 is a negative 28. All right. So, set each of those equal to 0. And solve for t. Add 1 to both sides and divide by 2. Over here, add 13 to both sides and divide by 2. And there are 2 potential solutions. So what do? We got to find out if they are solutions. So we go back to the original equation. Here it is. And all I want to know is t equal to 1/2, or is t equal to 13/2 solution? And I've got to substitute back into the original equation. Alright, so square root of 3 times, plus 2 times 1/2 plus the square root of 4 times 1/2 minus 1. Is that equal to 1? Let's just go ahead and do this one, and then we'll check the other. Well, the first radical, that's just 3 plus 1. And here, that's the square root of 2 minus 1. Equals 1. 3 plus 1, that's the square root of 4, plus the square root of 1, or 2 plus 1 equals 1. And it's true and true, so t equals 1/2 does not check. How about 13/2? Okay, that would be the square root of 3 plus 2 times 13/2 plus the square root of 4 times 13 halves minus 1. Again, I want to know, is that equal to 1? The halves, or the 2's divide out here, and so that leaves just the square root of 16. Over here, 2's again divide out, and so that leaves the square root of 26 minus 1. Or 4 plus the square root of 25, which is 5, which again is not equal to 1. So neither of these solutions work. So our solution set is the empty set, or that symbol also. Okay. Well, you knew it had to happen. Now we got 3 radicals in the equation. And let's solve for t. What do we got to do? Well, isolate a radical. Well, there's already one isolated, and it looks like the most complicated one, so why don't we just leave it like it is, and we're ready to square both sides. Huh? So inside, on the left side, in parentheses, I'm going to put both radicals, 2t plus 5 plus radical 2t plus 8 equals the square on the right side of the radical 8t plus 25. And now we got to square this sum, which happens to be, again, the same pattern, it just happens to have 2 radicals in it. So we could still use that same pattern. We square the first one. Well, you're squaring a square root radical, so you get just what's underneath the radical, 2t plus 5, plus twice the product of the 2, which just happens to be radicals. So that's 2t plus 5 times the radical 2t plus 8, plus the square of the second one. It's the square of the first one plus twice the product of the 2 plus the square of the second one, which again is a square root radical, so it's just what is inside the radical, equals the square of another square root radical, which is again just the radicand, what's inside the radical. Well, you can see you're still going to end up with a radical, because the square root of a product of the square roots is still a square root. It's the square root of the product. So this term right here is going to be a radical term. So I still have an equation with radicals, and so the method is to isolate that term. And I think at the same time I'm going to rewrite it as the square root of a product. So that's the term I'm going to isolate, and I think I'll just keep it on the left hand side and move everything else over to the right hand side. But before we do that, let's don't get in a big rush. Let's collect like terms. So I'm going to rewrite this as 2 times the square root of the product, and I think I'll just show that as the product of 2 binomials there, plus 2t plus 2t, that's 4t, and 5 plus 8, that's 13, equals to 8t plus 25. And now it's easy to isolate. We'll isolate, move these over to the other side. Subtract 4t from 8t, you get 4t. Subtract 13 from 25, you get 12. And you're left then on the left-hand side with 2 times the radical. And eventually I'm going to have to FOIL that out anyway, so we might as well do it now. So let's FOIL this out. 2t times 2t is 4t squared. 10t plus 16t, multiplying the inner and the outer and adding them together, 10t plus 16t is 26t plus 40. And now, notice that each term has a factor of 2 in it, so let's take advantage of that, and we'll divide this out, the 2. So on the left-hand side, I'm just left with the radical. On the right-hand side, I'll have then 2t plus 6. And now, we're ready to square both sides again, right? So everything in parentheses on the left, everything in parentheses on the right, and square both of them. You square a square root, you get what's underneath the radical. Square this binomial, again, you square the first one, then it's plus, it's that sign, plus twice the product. So you can just do it this way. Multiply those two together in your head. That's 12t, and double it, which is 24t plus 36. Okay. Looks like a quadratic equation, at least the first impulse. So I would think to set it equal to 0, but notice that the 4t squares are going to add up to 0. So it's really not quadratic, it's a linear equation. We're left with 26t minus 24t equals to 36 minus 40, or 2t is equal to a negative 4, or t is equal to a negative 2. Maybe. We got to go back now and check it. Where do we go? Back to the original equation. There it is, right up at the top. So let me just cover this up. I know what I think the solution is. T equal to negative 2. Let's find out. So we take the first radical, put a negative 2 in there. Take the second radical, put a negative 2 in there. Take the third radical and substitute a negative 2 into there for t. And the question is, do those equal each other? Well, on the left side, that's 5 minus 4, or the square root of 1. And this one is, again, a negative 4 plus 8. That's the square root of 4. And over here, you've got negative 16 plus 25, or the square root of 9. 1 plus 2 equals 3. You bet. And so this, it must be also then a true statement, which means this is in our solution, and that's the only thing in our solution, so therefore our solution set is a negative 2. Well, that last one was just about as bad as they're going to get as far as dealing with square root radicals go. You can expect in your homework to have maybe one with 3 terms in it, or 3 radical terms. But before you get too locked in or thinking that's the only kind of radical equations there are, let's look at 2 more examples and where they're not square root radicals. Take a look at this number 9 here. We've got cube root radicals. The cube root of 3x minus 4 equals the cube root of 2x squared minus 9. Same procedure. First we isolate a radical. Well, the way it's written, that's the only way to isolate. And now we want to use the property that we've been doing throughout, that if you have an equation, A equals B, that
a to the n equals b to the n is the transformed equation we want to take. We want to change this original equation to that. In this case, since it's cube root, what we want to use is we want to cube both sides, surely. So sure, that's what we're going to do. We're going to put everything in parentheses on both sides and cube it. It just happens that what we're cubing is a cube root. And when that happens, we know we get just what's underneath the radical. And so it comes out as a quadratic equation, which we know set it equal to 0. So subtract 3x from both sides, add 4 to both sides. If you add 4 to this, that goes away. Add 4 to this, you get minus 5. And right here you expect, if it comes out to be a quadratic, that this is going to factor. If it doesn't, probably something's wrong. Well, 2x and x, looking for a difference of 3. Well, probably have to write it like this then, right? And it has to be a negative 3, so minus and plus. There's negative 5x plus 2x, yeah. And so those two factors equal to 0, so one of them, those factors, has to be 0. Solve for x. 2x is equal to 5. X is equal to 5 halves. Over here, x is equal to a negative 1. And again, we want to check. So here's our original equation. Here's our two solutions. X equals 5 halves, or x equals, what was it? Negative 1, yeah. Negative 1. So take the original equation, 3 times 5 halves minus 4 equals the cube root of 2 times 5 halves squared minus 9. Let's see if that turns out to be true. Well, here on the left side, that's 3 over 1. So if you multiply those together, you're going to get the cube root of 15 halves minus, we might as well change 4 to 8 halves. And remember, this is question mark. Over here, we've got a square first, so if you square that, you get 25 fourths. Be careful there in the order of operations. So that's 2 times 25 fourths minus, well, I can see what's going to happen here. I'm going to divide out, and I'm talking about 25 halves, so change that 9 not to fourths but to halves is 18 halves. And so here on the left, I've got 15 halves minus 8 halves is 7 halves. And on the right, I've got 25 halves minus 18 halves is, again, 7 halves. And we come out with an obviously true statement. Even though this didn't turn out to be a perfect cube, it turns out to be exactly the same cube root radical on both sides. So this has got to be true, which means this has got to be true. So this is a solution. And the other one ought to be a little easier to check. It's the cube root of 3 times the negative 1 minus 4. Is that equal to the cube root of 2 times the negative 1 squared minus 9? Well, that's a negative 3 minus 4 is a negative 7. It's the cube root of a negative 7. And over here, you square negative 1, that's 1, times 2 is 2. So this side is the cube root of 2 minus 9, which is also negative 7. Oh, wait a minute, is that a real number? Yeah, remember it's cube root, odd root. It's okay to have a negative radicand with an odd root. So this is in fact, we can say it is the negative of the cube root of 7. Likewise, the same thing over here, and those are true, the same numbers, so this has got to be true, so this has got to be a solution, and so therefore our solution set, the solution set is 5 halves and negative 1. Not only square root, it's got fourth root. There's a nested radical. One may not be that clear on the screen. There's a radical within a radical here. So you got the fourth root of x plus the square root of x plus 4 equals 2. So the radicand under the fourth root radical is x plus the square root of x plus 4. Well, still, procedure is the same. You want to isolate on the radical, and the only radical you've got, radical expression or term, is that one right there, and use that property that if a equals b, then a to the n equals b to the n by raising both sides, in this case, to the fourth power. So I'm going to look at it like this. And so on the left side, I've got the fourth root of x plus the square root of x plus 4. And on the right side, just 2. And of course, if you take the square root of the fourth root of anything, you're going to get that radicand, whatever it is. So here, it's x plus the square root of x plus 4 equals to 16. And now we've got a rather basic radical equation, but it's with square root. So we just do the same thing. Isolate the radical by subtracting x from both sides. So if you take it away from here, leaves you just with that. Take it away from here, gives you 16 minus x. And now square both sides. Square the left side, you get what's underneath the radical. Square the right side, you're going to square this difference. So it's the square of the first term. Well, how do you square 16? 16 times 16, or 16 squared, is 256, minus this sign, minus the product of those two terms doubled, or twice their product. So multiply them together, that's 16x, double it is 32x, plus x squared. Quadratic equation, right? So set it equal to 0. So I'm going to make the left side 0 by taking away x. And at the same time, let's get this thing in the right order. I'm going to put the x squared term first. Then I'm going to take away x from this side. So it's gone. And I take away x from that side, makes that a negative. So it's negative 32x minus x is a minus 33x. And then take away 4 from that side, subtract 4 from that side, subtract 4 from this side, will give me plus 252. And I expect that to factor. Well, It's really one of the easy kind of factors, right? X and X, signs have both got to be the same. They got to be that sign. I'm looking for a product of 252 whose sum is 33. Well, we could spend time looking for it, but we know we can find it. It turns out to be 12 and 21. If you multiply those together, that's 252. If you add those together, that's 33. All right, so set each factor equal to 0. X equals 12. X equals 21. Maybe. All right, we got to go back to the original equation. Here it is. And we got to ask, is X equals 12? Or does X equal 21? Well, let's try 12. The fourth root of 12, wherever you have X, you're going to put 12, plus the square root of 12 plus 4. Is that equal to 2? We'll work inside, do the inner radical first. That's the square root of 16. I'll just write it down, which we know is 4. And 12 plus 4 is 16. And now you're going to take the fourth root of 16. And that is 2. And that's what we wanted. So this is true. How about 21? The fourth root of 21 plus the square root of 21 plus 4. Is that equal to 2? Again, same procedure. Start with the square root. That's the square root of 25. And the square root of 25 is 5. And that gives us the fourth root of 26. And that is not equal to 2, is it? So therefore this must not be true. So if this is not true, X cannot be 21. So our solution is only 12. Well, that concludes this video on solving radical equations, and I wish you good luck and hope all yours check.